Hello, my name is Parker Landon, and this is my Chemistry in the World World project for Chem 141. My project will be focusing on the gamma-ray attenuation lengths for aluminum and lead, and the practical applications learned from calculating these values. Before I begin, here's an overview of today's discussion. I will begin with an introduction to the Geiger-Müller tube and electromagnetic radiation. I will then go to my data collection and results, where I will then move to the course connections and applications in the real world, finally closing out with some conclusions. To begin, we need to talk about electromagnetic radiation. Electromagnetic radiation is another word for light radiation. For humans, we are able to see using visible light, but we also use radio waves to communicate and microwaves to heat up our food. Visible light is also important for us because we can use it to identify different elements. Each element has a unique fingerprint called a spectrum. These spectra are dependent on the locations of negatively charged particles we call electrons. The electrons are found in the shells located around the atomic nucleus in what we call orbitals. These orbitals can come in a bunch of different forms, but they are all dependent on the atom's quantum number. A quantum number is the expression of the quantized properties of the subatomic system. To simplify it all down, we can identify the types of atoms and their properties based on knowledge of their electron configurations or the distributions of their electrons. Here's an example of a multi-electron atom, or an atom with multiple electrons, which we call zinc. This device right here is a Geiger-Müller tube. This is what connects to the Geiger-Müller counter, which informs us of the amount of ionized energy in the area. Ionization energy is the energy required for an atom to discharge an electron. The atom losing the electron becomes more positively charged, and depending on the initial number of electrons, becomes a cation. The opposite of this, however, is the ion. The Geiger-Müller tube uses the photoelectric effect to detect these ionized electrons, as well as other ionizing energies such as gamma-ray emission. There are three main types of radiation. The first type is alpha radiation. This is when an unstable nucleus loses 2 protons and 2 neutrons and becomes a different element. The second is beta emission. This is when an unstable nucleus emits a beta particle, which can be either an electron or a neutrino. Lastly is gamma radiation. This is when an excited nucleus emits a high-powered photon. Each level of radiation increases in energy. Alpha has the lowest levels of energy, and therefore is the weakest particle emission. Alpha particles are pretty safe around humans, as they are too weak to pass through our skin. Beta particles are the next energetic emission, which are slightly more dangerous for humans, as longer exposures can damage your skin. Gamma radiation, however, is the most dangerous and damaging of the three. Gamma rays have so much penetrating power that they can completely pass through the human body. As they pass through your body, they cause ionization, which damages your tissues and DNA. These penetration powers are independent to the types of materials used. We call this the attenuation length. The attenuation length is the measured distance of material needed to stop an energetic emission. For example, lead has a higher attenuation coefficient or stopping power than paper or aluminum. This is an image of a commonly used gamma-ray emitting isotope called cobalt-60. This was the material I used during my data collection to test the attenuation rate of aluminum and lead. To begin testing, I placed the Geiger-Müller tube directly above the radioactive wafer filled with cobalt-60. I then took individual slabs of aluminum and lead and recorded the amount of gamma-ray emission. With the data I collected, I was able to calculate a fit for my points as shown here. This image contains my data from my first trial with aluminum. The x-axis denotes the amount of aluminum, and the y-axis is the number of gamma-ray emissions. Using dimensional analysis, or analysis through units, I was able to determine that my attenuation coefficient should be in units of inverse centimeters. Even though I was able to get a fit for the data, I had to confirm the validity of that fit. I did this by completing a statistical check using a Poisson distribution function, PDF, and chi-squared minimization. The black curve is a PDF, while the pink line denotes my chi-squared. The red and blue lines represent the 95% confidence range, and because my chi-squared falls within this range, I can safely assume that my data is accurately represented. I repeated this process for the attenuation of lead, and then I recompleted another set of trials for both to get the most statistically accurate approximation for both the attenuation coefficients. The fitting equation shown here allowed me to solve for the attenuation coefficient denoted by the Greek letter mu in the exponential. Trial 1 aluminum had an attenuation coefficient of 0.15 plus or minus 0.001 inverse centimeters, while trial 2 had 0.12 plus or minus 0.001 inverse centimeters. For lead, I got an attenuation coefficient on the first trial of 0.3 plus or minus 0.001 inverse centimeters, with the last trial of lead with a value of 0.5 plus or minus 0.001 inverse centimeters. This graph shows the accepted values of attenuation at different levels of emission. Our gamma radiation emission strength is about 1.1 mega electron volts. Zooming in, we can see the accepted mu values for aluminum fall around 0.162 inverse centimeters, and the accepted mu values for lead are around 0.689 inverse centimeters. Comparing my values to the accepted values, I took the fractional difference and found that my trial 1 aluminum had a difference of 7.4%, the second trial of aluminum had 26% difference, my first trial of lead had 56% difference, and my last trial of lead had 27% difference. So what does this really mean for us? In the real world, knowing the attenuation coefficients can help us understand what types of materials to use when working with radioactive materials. This is super important for us when we're looking into the safety of humans working with the materials, as well as the safety of the environment around them. Our class also briefly touched on quantum mechanics as well as atomic nuclear physics, and our final lectures will be dedicated to understanding electromagnetic radiation and other particle radiation. For me, however, understanding these concepts are foundational for both of my majors. In space physics, I need to know quantum mechanics and nuclear physics to conduct research on particles, and for my engineering degree, I need to work with different types of radio frequency control systems and understand electromagnetic radiation is the first part of that. This lab not only helped me understand more about electromagnetic waves, but it also taught me more about their applications in our daily lives. Thank you so much for watching this video, and I hope it was a helpful overview for atomic nuclear physics.